Thank you for the introduction. So let me dive in and by starting off with talking about how traditional query engines based on shared nothing architectures were built, right? So in these architectures, you have data that is partitioned across several servers, and each server is responsible for storage and compute of its own partition. Now, systems based on these architectures are simple and elegant and worked well when you had dedicated on-premises infrastructure. However, moving these systems directly to virtual machines in the cloud is not optimal because they have certain limitations that preclude them from being able to fully exploit the benefits of the cloud. So firstly, consider the following example. Let's say we have VMs, each of which has 4 CPUs and 2 disks. And let's say we have a workload that requires 50 disks worth of storage, but only requires 20 CPUs worth of compute for query processing. Right now, in order to support this workload, you would have to end up provisioning 25 VMs, resulting in a wastage of roughly 80 CPUs worth of compute. Right. Similarly, if you had another workload which was compute intensive and was operating on a relatively small amount of data, then you would instead end up wasting storage resources, right? So what's happening in both these cases is that there's a mismatch between workload demands and the configurations that hardware has to offer, right? Now, the second limitations of these architectures has to do with elasticity. Let's say that we want to scale up or down one of these systems by adding or removing virtual machines. Doing so could potentially involve reshuffling a large amount of data, and this is bad because the same nodes that are responsible for query processing are also going to be involved in this data reshuffle, and that would cause a hit in query performance, right? So the fundamental issue with these shared nothing architectures that is causing these problems is that there is a tight coupling between compute and storage resources. So the obvious solution to this problem is to decouple compute and persistent storage, and by doing so, you can independently scale compute resources in a way that is independent of storage capacity, and you can do so in order to better match workload demands without the need for data reshuffling, right? So to this end, in this work, we explore the various design aspects of building a query engine on top of disaggregated storage. We also analyze data from several production workloads on a real system and use that to gain deeper insights into these design aspects and also point out future directions of work that may be of broader interest to the research community. So the particular system that we focus on here is Snowflake, which is a popular data warehousing system on the cloud. It basically allows users to store their data and run SQL queries on it. Snowflake has been in production for over 5 years now, and today it serves several thousands of customers running millions of queries per day, operating on several petabytes of data. So all of the analysis in this work, including the plots that I'm going to show in this presentation and results in the paper, are based on various statistics that we collected from roughly 70 million queries executing over a 14-day period on Snowflake, right? So to give you a glimpse of some of the characteristics of these queries, let's look at the following scatter plot. So here, each individual point represents one particular query, and the x-axis represents the amount of persistent data read by the query, and the y-axis represents the amount of persistent data written. So if you look closely at this plot, you can see that there are 3 distinct classes of queries. Firstly, along the x-axis, we see read-only queries. So these queries typically have like very small output sizes, which are returned directly to the user and don't need to be persisted, right? Which is why the amount of persistent data written is 0. Similarly, along the y-axis, we see write-only queries, and in the middle, we see what we call read-write queries, right? And you can see that within each of these 3 query classes, the magnitude of persistent data read or written varies by several orders of magnitude. This plot here shows how these queries are distributed over time. So you can see that the orange curve in the middle represents read-only queries, and we can see that the load pattern of these queries is significantly more variable compared to the other classes. In particular, we see spikes during weekdays, during daytime hours, and this indicates that these queries are typically interactive in nature, right? So before diving into the various design aspects, let me give you a high-level view of Snowflake's architecture. So the key abstraction that Snowflake offers to customers for computational resources is called the virtual warehouse. So customers can create virtual warehouses and then submit queries for execution on these warehouses. Now, under the hood, each of these warehouses is implemented using a set of virtual machines, which perform distributed execution of the queries. So in Snowflake, different customers have different sets of virtual warehouses. Sometimes individual customers could spawn multiple warehouses each for different kinds of workloads, right? Now, in order to bypass the limitations of traditional shared nothing architectures, Snowflake decouples compute from persistent storage. So what this means is that instead of storing persistent data within the virtual machines inside the warehouses, it stores all user data inside a remote storage system like S3, right? So when queries run, they read their input from S3, do their processing, and write their output back to S3 if necessary. Now, in addition to intermediate data, several queries produce certain amounts of intermediate data that needs to be stored somewhere during the query execution process. So an example of this is if you're doing a distributed join or group by query, then the output of the mappers before it is consumed by the reducers is an example of intermediate data, right? Now, the intermediate data has more stringent latency and throughput requirements compared to persistent data, and unfortunately, existing persistent data stores like S3 do not meet these requirements, right? So instead of storing intermediate data in S3, Snowflake uses a custom designed ephemeral storage system that is co-located with compute in the virtual warehouses in order to support low latency, high throughput exchange of intermediate data. So the ephemeral storage system in Snowflake has 3 key features. Firstly, like I just mentioned, it's co-located with compute in the virtual warehouses. So designing a purely DRAM-based system would be simple and high performance, but it would not be sufficient to support the diversity of workloads that Snowflake sees. Hence, the system in Snowflake uses both DRAM and local SSD resources within the virtual machine instances. So queries first write their intermediate data to DRAM until that capacity is exhausted, and when that happens, intermediate data is further written to local SSD. Now, in some cases, when even the local SSD space is exhausted, the data is further spilled to S3. This basically allows Snowflake to handle even queries that produce enormous amounts of intermediate data, right? So the second key feature is that in addition to storing intermediate data, the system also opportunistically caches a certain amount of persistent data. And this allows it to basically hide S3 access latencies, hence improving query performance. The third key feature is that although the ephemeral storage system is co-located with compute, Snowflake is able to use some techniques to support is still able to support elasticity without the need for excessive data reshuffling, right? So I'll talk a little bit more in detail about the latter 2 points in upcoming slides, but before that, let's look at some of the characteristics of intermediate data from production workloads, right? So this scatter plot here shows the different queries with the x-axis showing the total amount of CPU cycles consumed by each query, and the y-axis showing the amount of intermediate data exchanged, right? And we can see 2 things from this plot. Looking at the y-axis, we see that intermediate data sizes vary over several orders of magnitude, and also that there is not much correlation between the amount of intermediate data generated and the total amount of CPU resources consumed by queries, right? Similarly, if we look at a similar plot just with the x-axis changed to the total amount of persistent data read instead of the total amount of CPU cycles consumed, we see a similar trend. And what this indicates is that intermediate data sizes are typically very difficult to predict upfront, right? Now, given that the ephemeral storage system, which is storing intermediate data, is co-located with compute, it brings back some of the issues of shared nothing architectures. Like I mentioned before, Snowflake is able to use some techniques to avoid the elasticity issue, but the hardware workload mismatch issue is still unfortunately there. And that's especially prevalent given the large variation in intermediate data sizes independent of compute resources used, right? So fortunately, since the time Snowflake was originally designed, network speeds have significantly improved over the past couple of years. So we believe the possibility of trying to decouple compute and ephemeral storage also, in addition to just decoupling compute and persistent storage like it's done today, is an interesting direction to explore. So given this large variability in intermediate data sizes, the peak demand for intermediate data capacity over time is significantly higher than the average in practice. Snowflake exploits this property in order to opportunistically cache persistent data files within the ephemeral storage system. So by doing this, it's able to hide S3 access latencies and improve query performance. Now, when talking about caching, the obvious question that comes up is how to ensure consistency, right? So firstly, in Snowflake, each persistent data file is mapped to a unique node within the virtual warehouse. And this is done using consistent hashing over the file names. So what this ensures is that no 2 nodes can concurrently access the same file, and that precludes all of the consistency issues that arise from that, right? And secondly, the cache is write through in nature, and this ensures that the local copies are consistent with the copies in S3, right? So in the paper, we have more detailed analysis of how caching actually works in practice, and we also point out several interesting future directions of work in the context of caching on top of disaggregated storage. So in the interest of time, I'm not going to go into details of that here, so please refer to the paper if you're interested. So now that we understand how storage works within each virtual warehouse, let's look at how Snowflake handles elasticity, right? So firstly, elasticity of persistent storage is easy because it's just offloaded to S3. So systems like S3 today already support fine-grained elasticity of like storage capacity, and there's nothing special that Snowflake needs to do here. In order to achieve elasticity of compute resources, Snowflake uses a pool of pre-warmed VMs. And so what this means is that when it receives a request from a customer to scale up a warehouse, it takes additional virtual machines from the pool and allocates them to the warehouse. Similarly, when a scale down request comes, it takes VMs away from the virtual warehouse and puts them back in the pool, right? Now, the key challenge to achieving warehouse elasticity in this fashion is that because the ephemeral storage system is co-located with compute, you end up with the problem of data reshuffle during elasticity that we saw in traditional shared nothing architectures, right? So let's say that you have the following warehouse with 3 machines, each of which is caching a set of files, and you add one extra VM in order to scale it up. Now, if you were to naively implement elasticity in order to maintain the consistent hashing invariant, you would have to end up reshuffling a lot of cache entries, right? So the way Snowflake resolves this challenge is using a simple technique called lazy consistent hashing. Before I get into this, let me say a couple of words about how task scheduling works in Snowflake. So like most query engines, Snowflake performs locality-aware task scheduling. What this means is that compute tasks involved in query processing are scheduled onto nodes in such a way that they end up being co-located with the cached persistent data inputs, right? So in this example, if F4 is cached on node 1, F2 is cached on node 2, and F3 is cached on node 3, if you have a task T2 which is reading F2, it would end up getting scheduled on node 2. And similarly, if you had a task T3 that is reading F3, it would get scheduled on node 3. Now, with this in mind, let's look at how lazy consistent hashing works. So when the warehouse is scaled up by adding an additional VM, consistent hashing would dictate that some subset of the files cached on the first 3 nodes would have to be mapped to the newly added virtual machine, right? Let's say F4 is one of these files. Now, instead of immediately reshuffling these cache entries, which would involve moving F4 from node 1 to node 4 and several other files, Snowflake waits until a task that actually reads F4 arrives. When this happens, it schedules that task onto node 4, which is where F4 is actually supposed to be. Now, even though F4 is not actually present in node 4's cache, we can exploit the fact that a copy of it is available in S3, right? So task T4 directly reads F4 from S3 and then subsequently puts it into node 4's cache, right? So by relying on this kind of mechanism to lazily and eventually reach a correct state, Snowflake is able to support elasticity of warehouses without excessive data reshuffle. Now let's quickly look at the extent to which customers exploit elasticity in the wild from production workloads. So this CDF here shows the maximum warehouse resize across customer warehouses. So the x-axis is basically the ratio of the maximum warehouse size over the entire duration by the minimum warehouse size. And on the y-axis, you have the fraction of warehouses, right? So what we see from this plot is that close to like roughly 20% of warehouses that we saw exploit elasticity, and sometimes the magnitude of resize is as large as 100x, right? So there are 2 aspects to elasticity. The first is the resize factor, which we saw in the previous slide, and the second is the time granularity at which resizing happens, right? So in order to better understand the latter, let's look at the following elasticity profile of highly active customers in Snowflake. Right. So this plot basically shows the warehouse size as a function of time, and you can see that it varies from a minimum of like 4 nodes to a maximum of 32 nodes over time, right? And the plot below this shows the variation of actual query load over time measured in terms of average inter-arrival rate. And what we see from both of these plots is that the granularity at which warehouse elasticity is happening is significantly higher than the granularity at which changes in actual load happen, right? So the takeaway from this is that we really need mechanisms to support finer grained elasticity in order to better match demand. So to understand more holistically what the impact of the lack of fine-grained elasticity is, let's look at the system-wide resource utilizations in Snowflake. So this chart shows the average utilizations of CPU, memory, network TX and network RX across all machines that are active in Snowflake. And what we see from here is that there is a significant gap or there is significant room for improvement across all resources. And this is not surprising given the way the virtual warehouse abstraction in Snowflake is implemented today, right? Since each individual warehouse is given an isolated and separate set of VMs, this leads to the classical performance isolation versus resource utilization trade-off, right? Now, there are two solutions to two approaches or solutions to improving utilization. The first is to try and achieve finer-grained elasticity with the current isolated warehouse design, and the second is to move to a resource shared model, right, where resources of warehouses can be shared across multiple tenants. So there are several challenges to achieving fine-grained elasticity, and even if we could do it, there is another issue that is caused by a recent trend, which is making it difficult to continue with the current isolated warehouse architecture. So when Snowflake was originally designed, this is how the pricing model looked like. It would charge customers on a per hour basis for warehouses, and Snowflake would get charged by the cloud provider like AWS on an hourly basis for the VMs, right? And when this was the case, maintaining a pre-warned pool of VMs for elasticity was cost effective, because as long as one customer used a VM during a particular interval, you could just charge that customer for that interval, right? However, there is a recent trend where cloud providers have moved to per second pricing. And in order to stay competitive to customers, Snowflake had to immediately change its pricing model to a per second granularity, right? Now, with the move to per second pricing, maintaining a pre-warned pool is becoming increasingly less cost effective, and that undermines the viability of the first solution, right? So that leaves only the second solution on the table, which is to move to a resource shared model, right? Now, by moving to a resource shared model, you would have multiple benefits. Firstly, you'd be able to improve resource utilization by statistically multiplexing demands across customers, and also be able to support better elasticity using the same technique, right? So we have more details about providing more evidence of how statistical multiplexing could actually enable this in the paper, and I'm not going to go into details in the interest of time. So while moving to a resource shared architecture could certainly improve resource utilization, it comes with one key challenge, which is that we need to ensure the same or similar isolation guarantees as what the system provides today, because this is a very important requirement in Snowflake. So there are several challenges to doing that. In particular, the two key resources in warehouses today are compute and ephemeral storage. While Snowflake could leverage the large amount of work that has already been done in terms of sharing compute resources, we believe there's more work and challenges that need to be addressed in the context of sharing ephemeral storage, right? So in particular, one of the issues that comes up is that of sharing cache. Given that cache entries have no predetermined lifetime, even if one particular tenant was not actively using a particular cache entry, we cannot take this cache entry away and give it to another tenant, because we cannot predict when the first tenant will re-access the data entry, right? And in addition, there's also an issue with supporting elasticity without cross-tenant interference, because if you try to scale up a shared warehouse, which multiple tenants are using, then you might, if you do it with the current mechanism, you might end up triggering lazy consistent hashing for files of multiple tenants, which is violating the isolation guarantee too, right? So we ideally need mechanisms to provide private address spaces for tenants. So in conclusion, we've explored various design aspects, provided data-driven insights, and pointed out directions of future work in the context of query engines on top of disaggregated storage. Although we focused although most of our findings are from a particular system, which is Snowflake in this work, we believe that many of our findings are more generally applicable to query engines and possibly even general distributed systems built on top of disaggregated storage. So the data set that we use containing statistics of 70 million queries from production has been publicly released. You can find instructions to download and scripts to analyze in the following GitHub repository. And we think we've only scratched the surface in terms of the analysis that we can do with this data set, and we're excited to see what new insights the community can bring. So with that, I would like to conclude and would be open for questions. Thank you.